Okay, so next lecture is about frequency filtering. So let us go to the whiteboard and see a bit why we can do that. Contanos si te anda.
Vale, a ver. Coge un niño y llega súper emocionado y dice, super, oye, papá, hoy he engañado al conductor del autobús. Y mi padre coge y dice, a ver, ¿qué has hecho? Y entonces le dice el niño, pues le paga y luego no me cuenta papá. Y mi padre, pues, ya está.
Bueno. Okay, so why we can do filtering in Fourier space? The reason, I will explain it in one dimension, that is simpler to write the equations, but the same idea extends to two dimensions. So we were seeing yesterday that we can compute filters by applying a kernel, to the input image. So this would be the input image. This would be the input image. This would be the output image. And then if we convert the input image with the kernel, then we can, for instance, average locally pixels.
No se importa.
Darme cuenta no anda.
Vale. Esto es un señor que llega borracho a su casa y le dice a su mujer, ¿de dónde vendrá Paco? ¿De dónde vendrá Paco? Y dice, ¿de dónde viene Paco? ¿De dónde viene Paco? No sé.
So we may use a kernel to compute averages, and the kernel to compute averages typically they look something like this. So this is n, this is h of n, and then we have our examples here. So these are the typical kernels to compute averages. So for instance here the height has to be 1/5 because we have 5 samples. And we can also compute derivatives or detect borders. So we saw these are the kernels that can compute derivatives. And just a reminder, when we were computing these convolutions, so we were having this kind of expressions. So when you convert with this, what you get is something like, now I will do it with images, but you get something like this. So you are taking, this one is coming from this one is coming from this. And then it depends on which direction you are doing the negative delta. You will have RC plus 1 or R minus 1C or R plus 1C. So it depends on where you put the negative delta. Okay, but this is when you do the convolution in real space, but you can also do the convolutions in Fourier space. So in Fourier space, if we now take put it like this, we take this expression and you compute the Fourier transform of that expression, then what you have is that the Fourier transform, that for us it is a two-dimensional signal, but let's write it in 1D, that is simpler to write. So the Fourier transform of the output image is the Fourier transform of the input image multiplied by the Fourier transform of the kernel. Okay, so this is the Fourier transform of the input, and this is the Fourier transform of the kernel. So this is just the convolution property of the Fourier transform. So convolutions in real space imply multiplications in the Fourier space. Okay, so let's do that. Actually, that is one of the main kind of works that you can do with images. So very often you work with images in the Fourier domain, and very often you do this kind of works. Okay, so what we have been talking is about this property here. This property is the opposite. So this is the dual of the convolution theorem of the Fourier transform. Because of the duality between real space and Fourier space, so look at this one. If you convolve in real space, you multiply in Fourier space. And the dual, if you multiply in real space, you have to convolve in Fourier space. Okay, so this one is called windowing. This one is called filtering. So a window, you're applying the window G on the input function F, the input image F. Okay, but for the moment we don't need the windowing theorem. Okay, so for instance, let's put some examples. So let's say that we have this image, we have this kernel, and we want to convert these two images, and we want to do it in Fourier space. So first of all, you make the two images to have the same size. Otherwise, the multiplication is not well defined. So you expand the kernel to have the same size as the input image, and then you do the Fourier transform of the image, and you know now that what we are representing there is the amplitude, so the magnitude of the Fourier coefficients. And you do the same with the kernel. Now you multiply, but you multiply as complex numbers, not only as magnitude. So here we have a set of complex numbers, and you do the inverse Fourier transform, and this is what you get. So what about this filter? This filter is a band-pass filter, a low-pass filter, a high-pass filter. How do you know?
It's exploring the details.
So yeah, you can look at the output and you see a blurring, so it is a low pass. And how can you know in the Fourier space that it is a low pass? Because at the origin it is not zero. So at the origin it has a value, it has a high value at the origin, so it cannot be a low pass filter. It cannot be a high pass or band pass filter. Okay, good. So yeah, here you have more or less the pseudocode to do that. And yeah, the idea is relatively simple. So all this part up to here is just to construct the kernel. So you have an input image, and then you draw your kernel, and all this part, what it is doing is what I just said. So making sure that the kernel has the same size as the input image, and then copying the kernel in the middle of the large image. So it is just making sure that the kernel has the same size as the input, and that the kernel is at the middle of that. Okay, so this is from here to there. And then you do this is a little bit counterintuitive because we are shifting in the real space. Okay, so the result of this operation is the following. So we have seen the FFT shift as an operation to center the Fourier transform, but you can also do it in real space. So let's say that you have your kernel here. This is your image H, and you have your kernel here. So This part is full of ones. And let's put names to the axes. So this is the column axis, this is the row axis. If you want to put some other letters, this is typically X, this is Y. And then this is RC, sorry. Let's make it black. So this is Y. And then let's make it black. This is RC. Or you may also refer to it as 8 of YX. Okay, good. So now we do the FFT shift. FFT shift. That is an operation that we have seen in the Fourier domain to put the Fourier transform in the middle. The FFT shift is a, let me see if it uses FFT shift or, yeah, FFT shift. There is a very subtle detail between both, depending on what is the size of the image or whether it is even or odd. But think of it as the EFFT shift, as the FFT shift. So the output of this is this one. So before convolving, we have to apply that operation and identify why. The origin in this image is here. So this is, let's put it in a different color. So the origin is here. That is the 0, 0 point. But the 0, 0 point for MATLAB is always here in this corner. So before convolving, we have to put the origin where it is. Okay, so we have to do the Fourier transform of this image rather than the Fourier transform of this one. And then we are convolving the flower image. So we are convolving. So we have here the 1, 2, 3 flowers. But the origin of this image is also here. So the origin of that one, we don't care. The origin of this one, we do care, because you have to be very careful of making sure that the kernel is symmetric. And the kernel is symmetric if you don't do the FFT shift. The origin would be at this point, and then it is not symmetric anymore. You see? Okay, so that is why we are doing the I is inverse. So this inverse FFT shift. So when you go in one direction, it is called the FFT shift. When you go in the opposite direction, it is the inverse FFT shift. And then you do the standard thing. So you compute the Fourier transform of the image I, compute the Fourier transform of the image A, you multiply point by point. This is the new image, and then you do the inverse Fourier transform of this multiplication. And because in principle it should be a real image, but because of small numerical errors, you may need to take just the real part, because the imaginary part might be 10 to the minus 11. So those are very small numbers coming from numerical errors, but they shouldn't be there. Okay, so this is the way to convolve images in Fourier space using MATLAB. And yeah, here it is what I was explaining before, where the origin of your images are. So, for instance, for even images, so for MATLAB it is always there. So the 0, 0 is always there. So this point. And for you, probably, you tend to think of the origin being in the middle of the image, like for this kernel, circular kernel that we had before. So the middle of the image, we already know that it is defined as the integer part of the dimensions of the image. So for even, this is odd, for odd size images, it is very well defined. For instance, this image is 17 times 17, so you can put 8 pixels on one side, 8 pixels on the other side, and the origin is just in the middle. But if you have an image that has even sizes, then the middle of a pixel, you cannot define the origin such that it has 8 pixels on one side and the same amount of pixels on the other side, because otherwise you would need an odd number of pixels. So it has to be a little bit off center. Okay. And then this is the effect of the FFT shift. So for instance, if you define your kernel here or your kernel here, and you apply the IFFT shift, then this is what you get. And this is the same, but now with the smaller images. Okay, so now, yeah.
When is it one case and when is it the other one? When do we know that it's in the corners and when it's in the center?
So the origin for MATLAB is always in the origin, here in this picture, always. And it depends on how you have drawn your kernel. So if you draw your kernel in this way, that is the natural way for you, it is not symmetric for MATLAB. It is symmetric for you, but not for MATLAB.
Okay.
And MATLAB is just a tool, but in general, all image processing tools take the same kind of conventions. So this, if you use a library, a Python library or C library to compute your Fourier transform, they make the same assumptions. So, yeah. Okay, so, yeah, and also this is connected to something that you already know. You know that the fast Fourier transform is repeating your images, right? So before doing the Fourier transform, we are replicating it. So if you replicate this one, for instance, replicate it to the right, to the left. So you replicate it to the left, the 4 becomes close to the 5. That is what you wanted. You see? And when you replicate this to the top, the 2 becomes on top of the 5. That is what you wanted. So the replication that the FFT is doing is the one that requires to put the origin at that point. So let's use these frequency filters to compute averages. So the way we have seen to compute averages and before was this one. So you needed, or we knew how to come with this kind of filters, and if you want, we can also be a bit more creative and then give different weights. For instance, you can define a kernel that is like this. So let's say it is 1, 1/2, 1/4, and then you stop. So this is a blurry kernel that is giving more weight to the central pixel and less weight to the surrounding pixels. But aside from some easy schemes, it is rather difficult for us to come out with good weights, right? Okay, but the Fourier filter doesn't have that problem. So the Fourier filter, you can design your filter in the Fourier space and then do the inverse Fourier transform, and you will have the appropriate weights. So let's say an easy one. So for instance, let's say that this is our frequency. I always do the plots in one dimension because those are easier to make. But you can imagine that this has rotational symmetry. So this is. So if you want to make it 2D, you simply have to take this one and rotate rotationally, right? So this would be the ideal low-pass filter. And you know, when you do the inverse Fourier transform, what is that signal?
It's
The single. So there is a small detail. A sink, strictly speaking, a sink is. Let me do it here. And now we'll do it in a different color. So strictly speaking, but we are all loose with the language, right? So it is when you have this one. So this is a C, and this is omega C. I think the right expression is like this: the sine of 2 pi omega 0 t divided by 2 pi omega 0 t. Something of this sort. The important part here is this one. So that is sine of t divided by t. That is what makes the sink. What about this one? So this one, the inverse Fourier transform is not strictly like that. So let's say this is omega c. So it is something like sine of 2 pi omega c n, and then it is divided by another sine. And again, it is take this as approximate only, right? But the main idea here is you have sine over n, and then divided by sine. And there is some n also here involved somehow. Okay, so it is not exactly this, because this ratio would be 1, but there is something like, let's say. Sorry?
Without the sign beginning?
No, the discrete sign has this, because otherwise it wouldn't be periodic. It has to be periodic, I think. Well, something to look at, okay? But in general, you can think of it as a sink. Yeah, that is something strange here. Okay, so you can think of it as a sink. So that means that now you can have weights that are much more creative than what you can be with your weights, with the way you define the weight. So now your weight is something like this. So they oscillate. And you have appropriate weights just to select the frequencies you like. And you can define any function that has this kind of behavior, that has a high value at the origin, but then low value at high frequency. So you can put something like, this is omega, this is h of omega, and this is also a low-pass filter, right? And this is a low-pass filter that decays as 1 over omega squared, for instance, or 1 over omega, or you can define whatever function you like there. Okay, so what we are doing here. So we are. So when you average in the spatial domain, so you have to define the weights yourself. So you have to define the weights, and one of the constraints is that the sum of those weights has to be 1, because otherwise you're multiplying the energy of the signal by some value, not the energy, the central value. The central value, you are multiplying so the DC component of the image, you are multiplying by something. And when you do it in the frequency domain, you simply draw your function in the frequency space, you do the inverse Fourier transform, and then you have your weights. And one possibility would be 1 over omega. Or this omega is the module of your frequency. Okay? So this would be the function. And then you have much more creative weights. And what about high-pass filters? So high-pass filters when you do it in a spatial domain, each pixel is the difference between itself and a weighted average of its neighbors. So the kind of filters that we were seeing to compute derivatives in real space. So, for instance, let's see here. So let's look at this. So it is defined as a local average. So it is the difference between the current pixel and the local average of its neighborhood. So here the neighborhood is very simple. It is just one pixel. Here the average is just one pixel, but on the other side. So this is the pixel on the left. This is the pixel on the right. That is the way we have defined the neighborhood. Now we have defined the neighborhood with the pixels on the left and the pixels on the right. And you see, this is a kind of local average between, you can express it like that. And it would be the same if instead of that filter, you use this one. So let's go here, where you see better the effect of local averaging. So we have this filter. So the image C was twice I RC minus I C minus 1 minus I C plus 1. And this was our neighborhood. This is our neighborhood. Okay, so, but I can also, I would have exactly the same image if I do it in this way. RC minus 1 half of I RC minus 1 plus I RC plus 1. And now you see better. So I have the current pixel and I have a weighted average of the neighborhood. And this is the way to compute borders. And any other possibility that we saw is the same. So divide this by 4, then you have the central pixel, and then minus a local average of the neighborhood. And if we use any one of these ones, for instance, 1, divide by 8, then you have the central pixel, and then a local average of the neighborhood. So an edge detector in general, it is this. It is a central pixel minus local average of the neighborhood. But again, the way to define your weights, we are not very good at choosing numbers, right? But now when you are in the Fourier domain, you are not constrained to that anymore. So for instance, let's do it in 1D again. So let's say that I have and let's do it in for continuous images. So I want to compute the derivative of this. what is the Fourier transform of this? So when you do the Fourier transform, what do you get? So this j omega times x of j omega. So this is your filter. This is h j omega. And if I draw how this filter looks like, this filter, the module of this filter looks like this. This is omega. And this is omega. So the module of this is just the absolute value of omega. And so if this graph, I think, defines what are the properties of a differentiation in Fourier space. So differentiation is something that removes the low frequencies and boosts the high frequencies, and there is kind of a smooth transition between the two. And actually, there is a very nice property of these things. Sorry, this is not only one. So let's say that I want to compute the second derivative of an image. What is the Fourier transform of that? What do I need to do?
2 times.
2 times this thing. So it will be j omega applied twice. And then if you plot this filter, it's something like that. And this is omega squared. This is the module of j omega. This is omega. Okay, so differentiation in the Fourier space is just multiplying by a monomial of degree, the number of times you want to differentiate. And now it comes the nice thing. Okay, so you know how to compute the first derivative, the second derivative, the third derivative of a function. What about the 1.5 derivative? Can you define how to compute the 1.5 derivative? You can do it in Fourier space. Because in the Fourier space, if I want to compute, let's go to that. If I want to compute the alpha derivative of this function, and alpha now can take any real number that I like, 1.5, 1.2, whatever. All I have to do is to multiply by this polynomial. So now I have a fractional calculus. So I'm not restricted to the first, second, third derivatives anymore. I can compute derivatives of any degree. Okay, but in general, edge detectors and high-pass filters and derivatives, they are all related. So it is just removing the low frequencies, boosting the high frequencies, and we can do that in our Fourier transform. So we can decide, that is the one that is in the slide, we can decide that our filter is equal to alpha, let's use a different letter, omega. And omega is the frequency. And if you are in 2 dimensions, it is the module of that frequency. So it is just multiplying in absolute value. So we may decide to do that. And if you do the inverse Fourier transform of this, you do the inverse Fourier transform, then what you get are the appropriate weights. And the appropriate weights would be something like this. So that is one constraint. That is, this is H(n). So the zero frequency has to be removed. And the zero frequency, you may remember, this is the sum of this. So for a high pass filter or a one pass filter, that has to be zero. Okay, so the addition of all these samples, has to be zero. Okay, so that is what we have done in the slide. So in the slide, we have chosen the filter alpha omega. And this is just a reminder of how to make the filter. So you want to compute the filter of F with the kernel G. So you do the two Fourier transforms, and then once you have multiplied in the Fourier domain, you do the inverse Fourier transform to get the filter image. Okay, so let's say some examples. So we have here the ideal low-pass filter. So the ideal low-pass filter is in the frequency space. It is a step function. So it is 1 at low frequency and 0 everywhere else. If you do the inverse Fourier transform of this would be the point spread function. This is h of n. This is h of omega. Okay, so this is in Fourier space, this is in real space. This is the kernel in real space. And here we have representation of both in the same plot. This is a bad practice in general, but yeah, they have done it. So we have represented in the same plot the frequency response in red and the spatial response in black. Actually, in 2 dimensions, this function is not a sink. It is something called, let me do it here. So in 2 dimensions, when you have this, you have this disk that is 1 here and 0 outside, and this is frequency. So this is omega x, omega y. The inverse Fourier transform is something that is called the kink. And it is called kink because it is a J-Bessel function. It is a J-Bessel function. It's a function of the radius divided by the radius, more or less. So this is the. So the only difference is that because you are in higher dimensions, you don't have a sign anymore, but you have this Bessel function.
In the J-Bessel function, the G, sorry, the negative values get up to 0. It doesn't affect that.
No, those are you really have negative values. It is like in the sink. In the sink, you have negative values.
In the case of, if you go back to the slide, the negative values are all the same in the spatial space.
No, this one, or I don't know if we are talking about the same thing, but this black is negative. And then this is positive, and then this is negative, and this is positive.
Yeah, the positives are, I get it.
I know how to represent that between 0 and 255.
Yeah.
You rescale everything. So actually, whenever you show an image, a real valued image, like this one that can have positive, negative value, whatever, you never show this image alone. So what you do is you rescale this between 0 and 255. So the maximum value will become 255, the minimum value will become 0, and that's what you show. Yeah. Okay, so here is another ideal low-pass filter, but now the cutoff frequency. The cutoff frequency is the maximum frequency that can go through the pixel through the filter. So you have this is the cutoff frequency here. So the cutoff frequency is now smaller, and this you already know from the uncertainty principle. If you are compactly supported in one domain, you have to be wide in the other domain. So this one is bigger in Fourier space, so it is narrower in real space. This filter is more narrow in Fourier space, so it has to be wider in real space. Okay, so here we have the result. So we take an original image, the power spectrum, the phase spectrum. Then we multiply by the ideal low-pass filter in Fourier space. This is the multiplication of the two in power. So in power is take. So without power, what you have is this relationship. It's the multiplication of the two. But now, if I want to compute the power, the spectral power is, this is, you remind it is for deterministic signals, right? But for deterministic signals, it is taking the amplitude of the Fourier transform and squaring it. And then this is x of the omega squared, and then h of. So what we are seeing in the slide is this one. It is always the power. And remind that typically, instead of this one, what we see is the logarithm of that. Okay, so this is the filter power spectrum, and this is the filter image. Okay, so this is in module squared, this is just the image. And here you can have the comparison, so you can see how it changes. Okay, so I think time to make a break. So next thing to see is the high-pass filter. So the ideal high-pass filter has a frequency response that is just the opposite of the ideal low-pass filter. So it is 0 at low frequencies and 1 everywhere else. And this is the appearance of the real space kernel. And this is a one profile. So you see that the central pixel has a lot of weight, but then all the neighboring pixels also have a lot of weight. And what else? Yeah, actually, let me write. Total, ¿verdad? Todo.
Y Alex, ¿no?
Todo.
Eso es meter una película.
Bueno, buenísimo, ¿verdad?
¿Puedes contarlo?
¿Os sabéis el chiste del zoo?
¿De qué?
¿Os sabéis el chiste del zoo? No, lógico. Dice la madre, tomamos la tarta de fresa y fresa se quedó sin tarta.
Well, okay, so let's say that we have a high-pass filter. We have a low-pass filter, I think. This is a low filter of omega. This is 1. So this is the ideal low-pass filter. So I can construct a high-pass filter that is just the opposite of that one. And that one would be, say, this would be 1 1 minus the low pass filter. Do you agree? Okay, so now let's do the inverse Fourier transform of this. So we do the inverse Fourier transform of this equation, and what we have is that the kernel of the high pass filter as a function of n is the inverse Fourier transform of 1, that is delta. That is delta of n minus the inverse Fourier transform of the low pass filter, and that is the same. Somehow that depends on omega and okay, so yeah. So actually the better notation is this one. So a high pass filter is a delta minus the impulse response of the low pass filter. And that is exactly what we were seeing in this slide. So what we are seeing is a delta minus a sink. Okay, so we apply that filter to an image. So this is the original image, this is the original power spectrum, this is the ideal high pass filter. And then when you multiply, this is what you get. So the low frequencies, the very, very low frequencies are set to 0, and then the high frequencies can pass through the filter. And this is the filter image. And this filter image, these kind of filters, they are also called notch filters. So a notch filter is one in which you are rejecting some frequencies, or in this case, the very low frequencies. And this star here is because just of your question before, Gonzalo. So when you have a high pass filter version of an image, you have positive and negative values. So here what we are seeing is just a remapping between 0 and 255. Yeah, so what we can see are the borders. So the borders of the image, because we know that the very low frequencies are the ones of very smooth details. So all the DC component of the image, so how intense it is in this loss. And then the very smooth details, like this one is a very smooth detail. It has almost disappeared. Okay, then ideal bandpass filter. So the ideal bandpass filter you can design as a low pass filter, a wide low pass filter minus a narrow low pass filter. So this one has a radius ρ1, this has a radius ρ2, and then the band pass filter is defined between ρ1 and ρ2. And here, yeah, and you can imagine the impulse response. So the impulse response of a band pass filter using the same trick that we had before, it will be this one. So the impulse response of a band pass filter is the sink of the y. The y was ρ1, I think. Let's go make a 1. Minus the sink of omega 2. So it is the subtraction of two sink. All this is in one dimension. In 2 dimensions, you know, we have the jinx of the sink. But okay, so this is the low pass filter with ρ1. This is the low pass filter with ρ2. Which one of the two is narrower in Fourier space? ρ1 or ρ2? ρ2 is narrower because the image is more black. Okay, so we have lost more high details, small details. And then this is the subtraction between the two. So it is 1 minus 2, and you get this one. So this is a bandpass filter, and you are focusing at some particular range of details. So you are losing the very low details, you are losing the very high details, and you are keeping details of some particular size. And this is the filter power spectrum. So this is the power spectrum of the filter. This is another example with now an narrower filter. So you see this one keeps more high resolution details than this one. This one is narrower, and we are just keeping kind of single wave. So only the waves with this particular frequency are kept in the image, and then this looks more like the patterns that we had for a single wave, right? But now in all directions. Okay, the optimal filter. So the optimal filter with respect to something. So you can be optimal with respect to some criterion. So the criterion in this case is the maximally compact support in both spaces, real space and Fourier space. So you may remind this uncertainty principle. That means that if you have a wide function in one space, or a narrow function in one space, it has to be wide in the other. And that was a lower bound for the support, for the multiplication of the support of the two functions. And you may wonder which is the function that has the minimum product of these two supports. So this is the lower bound. No function can have a product that is smaller than this. So, but which is the one that is closer to the bound? And that one is the Gaussian. So, yeah, this is the uncertainty principle again, just a reminder of what it is. So if you are very narrow in frequency, then you are very spread in real space. And in the direction, for instance, you know, those are two delta functions in Fourier space. So this is a cosine. So what we see is a cosine in real space that is infinitely supportive. And here we have very narrow support in this direction, but very wide support in this direction. So you have the inverse Fourier transform is this one, where you have a sine in this direction that is infinitely supportive, while in this direction you are very narrow, because here you are very wide. Okay, so why choosing the Gaussian? So the problem with the ideal low-pass filters and high-pass filters is that they have this sink behavior. So the sink behavior causes ringing. So for instance, let's say that you have this step function, you convolve with the sink, and this is what you get. And this is a bit unnatural. So after you want to remove the very sharp transition from black to white, but you don't want to create these ripples. So you look for some other filter, and the problem with the ripples, or the problem of the ripples, is caused by this very sharp transition in Fourier space. So I have a very sharp transition in Fourier space, and then that causes ripples in real space. And the way to avoid the ripples is to smooth the transition. So to have a smoother transition, not very sharp from 1 to 0, but going smoothly from 1 to 0. And the Gaussian is the one that minimizes this uncertainty principle uncertainty. So this product of the two supports in both the spaces. Yeah, so let's say that we have this Gaussian in Fourier space. The inverse Fourier transform of a Gaussian is another Gaussian. So it is a Gaussian in Fourier and a Gaussian in real space. And it is Gaussian, so meaning that there is no transition, or there is no zero crossing, so it doesn't go below zero, because it is a Gaussian. The Gaussian asymptotically goes to zero, but it doesn't cross it. So, yeah, this is the one-dimensional Gaussian. The main parameters of the Gaussian, you know, it is the location, that is the mu, and how wide it is, that is the sigma. And in 2 dimensions, you define the Gaussian in a similar way. So it is the multiplication of 2 univariate Gaussians. So once you have the univariate Gaussian, this is the Gaussian for one variable. So you multiply a Gaussian for the rows times the Gaussian for the columns. And this is one possible way. And these 2 Gaussians are independent. There are many other ways of defining Gaussian, and not many other, but a slightly more general way of defining a Gaussian. But this is a very simple one. Okay, and then you manipulate and you get this one. So this, if the mu and the sigmas are the same, then you have a relatively simple expression. And you take your image, you convolve with the Gaussian low-pass filter, and now you don't have ringing anymore. And you can compare with the ideal low-pass filter. This is ideal, this is with the Gaussian. So you have a smooth transition between black and white, but now the transition doesn't cause ringing. And you can have a Gaussian low-pass filter, so you have a Gaussian shape in the Fourier domain that translates into a Gaussian shape in the space domain. And these are just the central profiles of both functions. And if you have a wider support in Fourier space, then you have a narrower Gaussian in real space. So this is more close to, this is closer to a delta function. And here we have some examples. So let's say that we have this image. This is the original power spectrum. We multiply by a kernel that has this shape in Fourier domain. And then this is the multiplication. And yeah, the labels are inverted. But this is the filtered image. This is the original one. And we can define Gaussian high-pass filters just with this trick of 1 minus the low-pass filter. So I do 1 minus a Gaussian, and then what I have is a Gaussian high-pass filter. And what I'm convolving is delta minus the Gaussian response. So this is the delta minus the Gaussian. And here are the results. So this is original power spectrum. This is the shape of the filter in Fourier domain. And then we are multiplying, and then we have removed the very low frequencies, and this is the filter image. And depending on how wide your Gaussian is, you may keep more or less low frequency components. So for instance, this one was removing very few low frequency components, while this one is removing most of the low frequency components, not completely removing, but dampening them. And then that is why you have kind of the edges better highlighted. And you can define Gaussian bandpass filters. So you simply take 2 Gaussians of different widths, and you subtract one from the other, and now you have a Gaussian bandpass filter. And here is the low-pass filter with radius rho 1, the low-pass filter with radius rho 2, and you subtract 1 minus 2, and then this is what you get. And this is the filter power spectrum, the power spectrum of the filter. So this is H modulus squared. And here is the impulse response. So this is H of R and C. and this is a profile. So in the profile, you know it is the subtraction of two Gaussians. So it is Gaussian 1 minus Gaussian 2. So this is what you get, this black thing. So it is Gaussian 1 minus Gaussian 2. And in Fourier space, what you have is this kind of two lobes. And this is another example, but now with different sigmas. So now we have a wider Gaussian. This is what we keep, and this is the filter image. And here you have a comparison of ideal low-pass filters and ideal high-pass filters compared to the Gaussians. So you see, in the ideal, we see this ringing. You see the ringing here? But now in the Gaussians, you don't see the ringing anymore. And for the high-pass filters, you don't see the ringing so well. There is a kind of black ringing here. You can see. And then in the Gaussian high-pass filter, you don't see the ringing anymore. Yeah, this is the same. Yeah, with ideal bandpass filters, Gaussian bandpass filters. Yeah. Okay, so what about the power spectrum? So let's say that we have this image, and this is the power spectrum. So this is the module squared, and this is the phase spectrum. Then we multiply we blur with some kind of low-pass filter. So let's say it's a Gaussian one that produces this output. So the phase, so in amplitude, it goes to 0, but in the phase, doesn't go to 0. Actually, this is not a strictly speaking 0. Those are very small numbers, but those are not strictly 0. And you can try to figure out why. Why is that? So why we see the effect of the filter in the amplitude spectrum, but we don't see it in the phase spectrum? Okay, so let's think of it let's think of the equations. So again, I always do it in 1D because it is simple to write. Okay, so this is the filtering equation. Let's say that this is a Gaussian. So if it is a Gaussian, it goes to 0, but it never reaches 0. Okay. And this is a real value. This one belongs to real. So it is a real value number. So a real value number means that, let's say it is a number h. So what is as a complex, what is the module of h? This h. As a complex, what is the phase of h? What is the phase of h as a complex number? 0. So all real numbers, when considered as complex numbers, they have 0, all positive real numbers. Okay, so what is the negative? If h is negative, what is the phase of h? 1 negative. Okay, or minus pi or however you want to call it. Okay, so what I'm doing, this is a complex number multiplication. So this is module of xj omega times aj and the phase of x at that point times h, but h is just this one. So the multiplication of the two is you have to multiply this with this. So it is x times h, And then you have to combine this with this. So it will be AG, the phase of X, plus 0. So that means that the phase doesn't change, and the amplitude is the one that is changing. If H is a Gaussian. If H is not a Gaussian, then that's something else. If it is an ideal low-pass filter, it is the same, because the ideal low-pass filter is also a positive real number. So, but in general, it will not be the same. Okay, so that is why we see this. So we are seeing the power spectrum that is smoothly going to 0. At some point, we don't see it anymore, the small details there, but they are there. And the phase doesn't change. Okay, so this is the original image and sharpened image. Okay, so what is a sharpened image? So a sharpened image is, let's say that I take an image and I apply a high-pass filter. So if you take an image and you take and you apply a high-pass filter, what do you get? The borders, right? So you have the borders, let's call them Y. Y borders. And I do the following now. I take the original and I add the borders. This is the same. This is the same as doing this, as X of A times 1 plus high-pass. So what I have is an image with enhanced borders. And what is the shape of a filter that enhances borders? So it is 1 plus a high-pass filter. So for instance, one that could do that is this one. So it starts at 1 instead of starting at 0. Let's say that my filter is like we did before. So let's say that my filter is this one, 1 plus omega. So it's this one. So that filter keeps the low frequency component, but it is enhancing the borders. So those filters are called sharpeners. These filters are called sharpeners. Because they sharpen the borders. And we can see an example here. So this is the original image. This is the image with enhanced borders. Look at this one, for instance, here. You see? Any question?
¿Cómo se llamaban?
Sharpeners. O border enhancement.
Y también se podría hacer con las low pass.
¿De qué?
Con las que son bajas, las que son pero
También se podría hacer con la baja frecuencia, sí. Ahora podéis ser muy creativos. Ahora que tengo la herramienta de Fourier, ahora puedo diseñar en Fourier mis filtros como yo quiera. Y eso se traduce en pesos en el espacio real. Pesos que yo a mano no sabría poner, pero en Fourier es muy fácil ponerlo. Okay, so there is a funny demonstration I would like to do. And for this, I will ask you to go to the bottom part of the class. So go to the prayer part, all of you. Y miráis para allá. Porque tengo que buscar una cosa y si me lo veis. O miráis para otro lado. Mirad para allá. Mirad para la pared. Así no me veis lo que estoy buscando. No sé si va a salir. Me deja, pero bueno, da igual. Da igual, daros la vuelta. No sale, no tiene nada. ¿Qué imagen es esa? No, mirad esta de aquí. Mirad esta de aquí. Esta, todas las demás no se ve. En esta sí que se ve. ¿Quién es? Y ahora os acercáis. Claro.
Si lo pones.
Está este, ¿no?
Todo ya.
Son las gafas. Aquí no sale bien porque esta pantalla tiene muy buena resolución. Entonces no se ve tanto el efecto, pero con los proyectores se veía muy bien.
Ha funcionado con todos menos conmigo.
Pero, ahora antes de lo que está pasando ahí, lo que está pasando es esto. Tenéis un espectro en el que tenéis hasta aquí la imagen de este y aquí la imagen de medio.
¿Tú qué has visto?
Y esta sería la imagen. Entonces tú pones las bajas frecuencias de una y las altas frecuencias de la otra. Entonces si estás lejos, como tu ojo es un filtro paso bajo, o el proyector es un filtro paso bajo, lo haces así, te quitas Marilyn. Cuando estás cerca estás viendo las dos, porque ya ves todos los detalles. Bueno, con estas pantallas no sale.
Funciona.
¿El qué?
El 4K.
A ver, ¿qué le dices?
Me la voy a llevar como tele para casa. Porque tu mamá
Any questions? No question. Okay, so the exam will be until today. So probably this lecture we will not finish today. So if we finish, it enters. If we don't finish, it doesn't enter. Okay, so let's see. So next lecture is about sharpening. So sharpening, you already know the concept. So yeah. So this is computing a property that we will not see the demonstration. Okay. We will be happy with this. Okay, so happy with this reason. So let's start a new one. So we will be happy with this. Okay, so let's start with an image, with a signal. So let's say that we have f of t derivative. We do the Fourier transform. We already know the Fourier transform. This is this one. Okay, so this is for 1D signals, 1D continuous signals. Okay, so let's say that we have now a continuous image, I, x, y, and I want, let's think of what is the derivative. So you are at the point, x, y, and let's say that I want to compute the derivative along this direction, along the x direction. This is y, this is x. So I want to compute the derivative with respect to that direction. So what I will do is I will take 2 points. So it will be the limit when delta x goes to 0 of I of x, y, minus I of x plus delta x, y, divided by delta x. Do you agree? Okay, so, and I could do the same vertically. So I can compute the derivative in this direction. That would be the limit when delta y goes to 0 of I x y minus I x plus y delta y divided by delta y. Okay, so there are many samples. It's like this is the derivative when, from the right, and you know that you can compute the derivative from the left, and the point, the function is can be differentiated if the derivative from the right is equal to the derivative from the left. All these small details we are skipping. Okay, so and this let's put names. So this is the derivative I of xi. Now they are not anymore derivatives, but they are partial derivative of I xy with respect to y. And this one here, and this one here is the partial of I with respect to x. Okay. And I can do the Fourier transform of these two. So I can do the Fourier transform. And now the Fourier transform will be j omega x times n x, not x, I of a. This is a vector, you know that this vector is omega x omega y. And the same for this one. So what we are not doing is the proof that you get this result. But this is what you get. Okay, so then I could define now the derivative with respect to this direction, for instance, or any other direction. So once you have a 2D function, you can define the derivative with respect to any direction that you like. So let's say that this is the direction u that has two components, ux, uy. And now, how to define that derivative? So that derivative, that partial I x, we write it like this, that is more convenient. The derivative, this is the nabla operator in the direction u, is with the image I. This is just the same, okay, but a different notation, okay? You know the operator nada, right? From electromagnetics, for instance. No? No. And so the derivative in the direction u would be the limit. Now let me, when delta h goes to 0 of I x plus delta h ux. Sorry, this one doesn't have anything. Ux delta h y uy delta h divided by delta h. So you can define the derivative in any direction, right? And it would be the same as the other. So the x and y directions, they are not special.
And delta H is the like the green space.
Yeah. Delta H is in this direction, so it is a scalar. Here it was also a scalar. Okay, so and here comes the funny result. So the funny result is that this derivative, if I do the Fourier transform, yeah, actually this derivative can be without the Fourier transform. Without the Fourier transform, I can write it in this way: a partial of I with respect to x plus uy is a partial of I with respect to y. So you take the vector along which you are computing the derivative, then you take the x component multiplied by the derivative in x, the y component the derivative of y. So that means that actually if you want to compute, let me make the drawing again. So we have the image, we have the point, and we wanted to compute the derivative in this direction. So all you have to do is to compute the derivative in this direction, the derivative in this one. This one is ux, uy. So the derivative in this direction is a linear combination of these two other derivatives. And even there is a much more compact way to define this this expression. So this is ux, uy. This is a vector. Inner product with delta I, delta x, delta I, delta y. And what is the name of this vector? The gradient. This is the gradient of the image I. Laplaciano. No, Laplaciano es la segunda derivada, tiene que ver con la segunda derivada. Laplaciano. This Laplacian. The Laplacian of this is this one. So Laplacian has to do with the second derivative, and the gradient has to do with the first derivative. So this is equal to u inner product with the gradient of the image. This is a very, very nice result. So you can compute the derivative in any direction by simply taking the gradient, that is the derivative in x and y, and then computing the inner product with the direction you are interested in. Okay, so what does it have to do with the Fourier transform? So now, let's take that result. That is, let me write it again. So the gradient along the direction u of the image I is ux, and then the partial of I with respect to x plus uy, the partial of I with respect to y. And we do the Fourier transform. So we do the Fourier transform of this equation. So the Fourier transform of that equation is that the Fourier transform of this thing is ux, this is a scalar, times j omega x Fourier transform of I. So this the Fourier transform can be also represented with a hat plus uy j omega y and the Fourier transform of y. So now we can rewrite this as I, that is multiplied by this j ux omega x plus uy omega y. This is the Fourier transform of I times and the inner product of u multiplied by y. So this is an extremely nice result because we have generalized these results here, these ones here. So this was j omega x, j omega y, but now we understand why. This omega x is omega, the vector omega, multiplied by 1, 0. And this omega y is the vector omega multiplied by 0, 1. And then if instead of 1, 0, 0, 1, I take any direction, I simply have to multiply by the unit vector in that direction. So this is a very, very nice result. So now you can compute derivatives very easily in Fourier space by simply multiplying by this thing. Okay, so this is the proof of the results I have been. So this is the derivative along along y. Yeah, there is some factor here, 2 pi. It depends on whether you define it, you put 2 pi or not, but we don't care about these scalar factors. It is much more important the concept of the directions and the gradients and all that. So whether you have to multiply by 2 pi, if you want to be strictly correct, you have to add it, but otherwise the main ideas are the ones I have told you. And this is the same, so derivative in columns, derivative in rows, and then you have to multiply by the corresponding frequency. And you can, this is the Laplacian, actually. So the Laplacian, so for instance, let's say that I want to compute the Laplacian of an image. So the Laplacian of an image, you do the Fourier transform of the first term. The first term, the Fourier transform is 4 pi squared. U is the frequency in that direction squared. Then the Fourier transform of the image, and then the same for the other direction. Yeah, and you know, let's copy this result. So let's copy the main part of that result. So the main part is without constants. So what we have is the Fourier transform of the Laplacian, and also represent it like this. I'm using different notation so that you get used to the different ways of writing. Okay, so this is a differential operator applied to a function. And then the Fourier transform of this is, well, 4 pi. So you don't care about that. And then omega x squared plus omega y squared, and then the Fourier transform of the image. What is this? That is the module of the vector omega squared. So computing the Laplacian in the Fourier domain, it is extremely easy. You simply have to multiply by that. That you already know. This is what kind of filter? What is the shape of this?
Gaussian.
It's like that, right? So this is the filter, and this is omega. So it is a high-pass filter. So computing a Laplacian is simply computing a relatively strong high-pass filter. So the weakest one was this. That is omega. So this is omega. This is omega squared. So time to stop, I think. Bueno, pues no entra. Tenéis 2 semanas de aquí al examen.